Thank you for the introduction. Today I'm going to talk about our recent work understanding and modeling on-die error correction in modern DRAM, and this work was done by researchers in the Safari group at ETH Zürich. So I'm going to start off with a high-level summary of the talk. Our motivation for doing this work is that experimentally studying DRAM error mechanisms provides insights for improving performance, energy, and reliability. Unfortunately, on-die error correction, or on-die ECC, makes studying errors very difficult, and this is because it distorts the true error distributions that we want to study using unstandardized, invisible ECC functions. And this means that the post-correction errors that we observe lack the insights that we seek from the pre-correction errors. Therefore, our goal in this work is to recover the pre-correction information that's masked by on-die ECC. To this end, we propose three contributions. First, we propose EIN, or error inference, which is a statistical inference methodology that infers the ECC scheme used in a given device, including the type of ECC, the word length, and the correction capability of the code. It also infers the pre-correction error characteristics beneath the on-die ECC mechanism. And EIN does all of this without any hardware intrusion or other insight into the ECC mechanism. Second, we provide EINSim, which is an open source tool for using EIN with real DRAM devices, and EINSim is available at the following GitHub URL. Finally, we provide an experimental demonstration of EIN using 314 LPDDR4 DRAM devices, and we show that EIN effectively infers the on-die ECC scheme and the pre-correction error characteristics of real devices with on-die ECC. And we hope that both EIN and EINSim enable many valuable studies going forward. So I'm going to start off with some background about error characterization and on-die ECC. So what exactly is DRAM error characterization? Well, it's the process of studying how DRAM behaves when we deliberately induce bit flips. And we might study things like operating timing constraints, different error mechanisms and how they scale across different technologies, system-level interactions between the CPU and DRAM, and even environmental effects such as temperature and voltage. And our hope is that by doing all these studies, we gain some sort of understanding about how DRAM works, and from this, some exploitable insights for improving the system. So how do we go about characterizing DRAM? Well, we typically start off with a testing routine that follows a methodology as follows. First, we write data to DRAM, then we induce errors, we read the data back, and then we record the error locations that we observe. We typically feed this testing routine into some sort of tester, which can be, for example, CPU or FPGA, and the tester is typically connected to the DRAM device that we want to characterize. And the output of the testing routine is an error distribution. For example, it could be the spatial distribution of errors throughout the DRAM address space. It could be the temporal distribution of how errors evolve over time. It can look at the variation between different cells, and we can even compare different devices against each other. So now, why might we be interested in studying DRAM errors? Well, DRAM errors provide insight into how a DRAM device works, and this is because different error mechanisms are based on physical phenomena, and any patterns we observe in the errors can actually indicate opportunities for improvement. What we typically want is we start with some characterization-driven insights, and we can use this to improve performance. For example, prior works have used characterization-driven insights to reliably reduce conservative operating timings. We can improve reliability, for example, efficiently profiling for and mitigating errors. We can improve energy efficiency, for example, reducing the cost of refresh and other operations, and even security, for example, defending against security vulnerabilities such as rowhammer. There are typically three key types of DRAM that we might be interested in characterizing. The first uses no ECC, and this is your standard type of DRAM device. And here, the interface between the tester and the DRAM just exchanges the normal data. The second type of DRAM we might be interested in characterizing uses what's called rank-level ECC, and this type of device is typical of server-style systems. And here, the DRAM module itself is provisioned with an extra chip, which the tester may use to store error correction information. And in this type of system, the error correction logic occurs within the tester itself. The third type of DRAM device we might want to characterize uses what's called on-die ECC. This is also known as integrated ECC. And here, the error correction logic is located within the DRAM chips themselves. So when we connect this with the tester is able to write normal data to the DRAM device, but reads corrected information. So in terms of characterizing these three types of DRAMs, in the case without ECC, the tester can directly access the DRAM cells. For the rank level ECC system, the tester can also directly access the DRAM cells by simply bypassing the ECC logic within the testing device. However, for on-die ECC, there's no way for the tester to disable the error correction logic within the DRAM device, and therefore the tester can only access the DRAM cells through the ECC logic. Unfortunately, the on-die ECC schemes that are used today cannot be bypassed. They're unknown and proprietary, and they're also completely invisible to the rest of the system. So let's take a look at how ECC complicates the error characterization process. So I'm going to walk through a quick example here, and let's suppose we start off with some data that we want to write to the DRAM device. And here, let's assume it's a 4-bit vector consisting of all ones. So let's consider 3 different ECC schemes, A, B, and C. So the first step is to encode the original data in its error correction form. And so we pass this data through each of the different encoders, which results in the encoded data. Now let's suppose the encoded data is written into the DRAM device, but the DRAM device is faulty, and so errors occur. And for sake of example, the errors occur in the same bit positions in each of the 3 DRAM devices, in bit positions 1 and 5. So now, when we go and try and read out the data, we have to pass this information first through an ECC decoder. And let's assume this is a single error correction decoder. Unfortunately, in each of the devices, we have 2 bit flips, and so the error correction mechanism can't correct the bit flips that occurred. Instead, it'll perform some sort of undefined operation. And indeed, we see that for ECC scheme A, we observe 1 error. For scheme B, we observe no errors. And for scheme C, we observe 2 errors. And so the takeaway from this example is that the observed errors are not necessarily the bit flips that actually occurred within the DRAM memory itself. So now let's take a look at how this makes error characterization difficult. So let's suppose we want to characterize a DRAM device, and we start off with some pre-correction error distribution. Now this error distribution is based on a physical DRAM error mechanism that likely is well understood, and we know what to expect from this error mechanism. Now if we pass this through 3 different ECC schemes, A, B, and C, each of which are unknown, we end up with what are called post-correction error distributions. And these post-correction distributions look very different from the original distribution we started with, and they also look rather different from each other. And this is because the post-correction distributions are ECC scheme specific, and the influence of the original error mechanism that we started off with is potentially lost. So this causes 2 key problems for error characterization studies. First, it prevents comparing error characteristics between different devices that might be using different ECC mechanisms. And second, it obfuscates the well-studied error distributions that we're expecting from DRAM. So now let's take a look at a concrete example of how error correction may interfere with the study we're trying to do. And in this example, we're going to do a technology scaling study. So the goal of our study is to look at how errors evolve over different technology generations. And so I'm going to show some example data here. Along the y-axis, we're showing the testing parameter value, which might be different temperature values or voltage values. It's essentially the independent variable that we're controlling in our test setup. Along the x-axis, we show different technology generations. So let's say we make a measurement of the Gen 1 device. Here we see a distribution, and this distribution represents the distribution of all bit errors throughout an entire device. And we see that it spans the y-axis values from about 0.4 to about 0.8. So now if we go ahead and make a measurement of Gen 2 and Gen 3 devices, we see that these follow values that are lower on the y-axis. And so we observe some sort of trend here, which is going downward across generations. Now, this might be consistent with a particular physical phenomenon that we're aware of. For example, this might make sense because of process technology scaling. So if we go ahead and make a measurement of the Gen 4 and Gen 5 devices, we actually see that they diverge from this trend that we're expecting. And this is rather confusing because the DRAM technology itself should follow the physical error mechanism that governs it. And so it turns out that in this example, this divergent trend is an artifact of error correction. And this is because we're looking at post-ECC error distributions. Now, if we had a way to look at the pre-ECC error distributions, for example, using the EIN methodology that we propose in our work, we see that the pre-correction error distributions actually follow the trend line we're expecting. And thus, in our technology scaling study, we can conclude that DRAM is following the physical phenomenon that we're expecting. Therefore, our goal in this work is to recover the pre-correction error characteristics that are obfuscated by on-die ECC. So now I'm going to introduce EIN, which is the error inference methodology we propose in this work, and I'm going to first talk about the inference problem. So EIN is based on the key observation that DRAM error mechanisms have predictable characteristics that are intrinsic to DRAM technology. And as an example, I'm going to talk about data retention errors. So DRAM fundamentally stores data in leaky capacitors that are susceptible to various different charge leakage mechanisms. Now it turns out that the leakage rates differ cell to cell all around the device due to process variation. And this necessitates a periodic refresh operation, which periodically restores the charge in all of these cells in order to make sure we don't lose the data that we're trying to store. Now, by disabling this refresh operation, we can induce what are called data retention errors. And data retention errors are well studied and are fundamental to DRAM technology. Most importantly for our work, data retention errors exhibit predictable statistical characteristics. And here I provide two examples of such characteristics. First, we expect data retention errors to follow an exponential relationship, exponential bit error rate with respect to temperature. And second, we expect data retention errors to be uniform randomly distributed throughout the device. Now let's take a look at how we can use this to infer the ECC scheme. So what we want to do is we want to exploit the error characteristics that we understand in order to infer the ECC scheme used in a device with an unknown scheme. And the benefits of this approach are that it works for any DRAM that's susceptible to the error mechanism, and therefore it'll be independent of any particular device or manufacturer, regardless of what ECC scheme is used in the device. So here I'm showing a high-level block diagram of how a device with on-die ECC might work. And so I'm going to define some terms so we can more easily talk about this scenario. So if on a write operation, the CPU will write what's called a data word into the DRAM device, and the ECC encoder will transform the data word into a code word. Now this code word gets stored into the data store where errors may occur. Now when we do a read operation from the CPU, the data is read out of the data store, and we call this code word prime because it may contain errors. And the ECC decoder performs an error correction operation, transforming code word prime into data word prime, which is read by the CPU. Now if no errors have occurred, data word and data prime will be equivalent. However, if errors have occurred, then data word and data word prime may not be equivalent, depending on whether the error correction mechanism is able to correct the errors or not. So based on everything we've talked about so far, by experimenting with the device, we can observe the difference between data word and data word bar, because we simply write some data to DRAM and read it back. Based on what we know about the error mechanism, we can predict what will happen between code word and code word prime. And so what we want to do is we want to infer the entire path back from data word prime to data word and look at everything that happened along the way. And this would involve inferring the ECC mechanism and the error mechanism. So EIN's key idea is to use the predictable error characteristics that we understand in order to infer both the ECC mechanism and the pre-correction error rates. So now I'm going to formalize this process a little bit into a mathematical formulation that we can actually use to apply to a real experiment. So I'm going to start by defining some shorthand notation for all the different elements of this diagram. So first, W and W prime are random variables that represent all of the different values that data word and data word prime can take on. And so we can think of data word and data word prime as being sampled from the W and W prime distributions respectively. Next we have the ECC scheme, which we're going to call S, and finally the error mechanism, which we're going to call theta. So what we want to do is we want to model the entire DRAM transformation as a function, and we call this function f. And f accepts W, which is the distribution of different input values we send to the DRAM, S, the ECC scheme, theta, the error distribution, and W prime, which is the distribution of outputs that we read from the DRAM. And the statement of the problem is that we want to infer S and theta given a measured W and W prime. I've reproduced the equation here for reference, and now I'm going to talk in a little more detail about what each of these variables represent. So we start with S, which represents the ECC scheme, but more specifically it represents the ECC encoding and decoding algorithms. So essentially the transformations from data word to code word and code word prime to data word prime. Theta represents the spatial distribution of errors, and if we're considering data retention errors, for example, we might use a uniform random distribution. But if we're considering a more complex error mechanism, we may also have to consider a more complex spatial distribution. Finally, W and W prime are the probability that the data word and data word prime are equal to any of the values they can take on. These values could be 0, 1, 2, all the way to the maximum possible value. And one thing to note is that W is typically defined by the data pattern that we write to DRAM. For example, if we write all zeros to DRAM, then the probability that the data word is equal to 0 is 100%, and the probability that it's equal to any other value is 0%. So unfortunately, it turns out that W prime is rather hard to measure. And for example, if we use a 64-bit data word, there's 2 to the 64 possible values that it can take on. However, a typical 8 GB DRAM device only has about 2 to the 30 ECC words in total. And this means that even if we read every value in the DRAM device, we're going to have a really hard time getting a representative sample of the W prime distribution. Instead, we define Wn prime, which is the probability that W prime has n errors, where n can range anywhere between 0 and the length of the data word. And this has 2 key benefits. First, it is easy to experimentally measure because we're simply counting the number of errors that occur in each data word. Second, it's very meaningful in the context of ECC because, for example, an n error correction mechanism will have a probability of 0 for every 0, 1, 2, all the way to n-bit error. Now let's take a look at how we can put this together into an inference problem. So what we want is that we want the most likely ECC scheme given a particular experiment. And so we can express this as P of S given X, where S is a particular ECC scheme and X is a particular experiment, including the error distribution and the inputs and outputs that were used during that experiment. Now, this gives us the probability of a single ECC scheme. And what we really want is we want to consider many different ECC schemes and choose the one that has the highest probability. So what we can do is we can take the argmax of this expression, and the maximum value will be the one that's the most likely ECC scheme. So unfortunately, it's not very easy to experimentally measure this quantity for many different ECC schemes because we only have a device with one specific ECC scheme available to us. So what we can do is that we can apply Bayes' theorem to flip this probability around. And so now we have an equation consisting of 2 different terms. The first term is called the likelihood distribution, and it asks the question, are these experimental results reasonable given a particular ECC scheme? And the second part is called the prior distribution, which asks the question, how likely is this ECC scheme in the first place? So this is called a maximum a posteriori or map estimation problem. And in the paper, we provide a rigorous derivation of this formula, and we provide the full optimization objective function that we use. And we also provide an extension for inferring the error distribution characteristics, theta, in addition to just the ECC scheme as shown here. So we can put this all together into a methodology, which we call EIN, or error inference. And EIN consists of 4 key steps. First, we define the experimental inputs, which are essentially the data pattern and the error mechanism that we're studying. The second step is to identify candidate ECC schemes that we feel might be used in our device. Third, we run experiments using the real device. And fourth, we compute the map estimation, which yields the most likely ECC scheme that's used in our device. So now, let's take a look at how EIN looks in practice, and we'll introduce what EINSim is and how it's used. So, map estimation in practice begins with the first step, which is defining the inputs. And so here we define the inputs as the data pattern and the error distribution we're going to study. Second, we enumerate a list of suspected ECC schemes, and we're just going to call them A, B, C, D, and so forth. And we can go ahead and apply the inputs and calculate what the output distributions would look like. And this output distribution is rather simple. It's just the number of errors per data word, right? It's the Wn prime distribution. The third step is to run experiments with a real device. And so we're going to test a DRAM device with an unknown ECC scheme. And when we do this, we apply the inputs, and this yields a set of observations, which are measured in the same way as the outputs from our calculation, essentially the number of errors per data word in the output. Now the fourth step is to compute the map estimation, and this yields a likelihood value for each ECC scheme we're considering. And so here in this example, we see that D turns out to be the most likely scheme because it has the highest likelihood. So one thing to note here is that it's actually hard to calculate the output distribution analytically. And so instead what we do is we use Monte Carlo simulation. And this is where EINSim comes in. So EINSim is a tool for using EIN, and it essentially evaluates the map estimation using Monte Carlo simulation. And EINSim effectively simulates the life of a data word throughout a real experiment and contains many different configuration knobs to try and replicate a real experimental setup. So EINSim is very flexible and extensible and applies to a wide variety of DRAM devices, error mechanisms, and ECC schemes. EINSim is an open source tool that's available at the following GitHub URL, and we also provide the example datasets that are generated using EINSim itself, and they're the same ones that we use in the paper. So if you're interested, please give EINSim a try. So finally, I'm going to talk about our demonstration using real LPDDR4 DRAM devices. So our methodology for experimentation is as follows. We experimentally test LPDDR4 DRAM devices, and we have access to 232 devices with on-die ECC and 82 devices without on-die ECC. We perform all of our testing in a thermally controlled testing chamber between the temperatures of 55 and 70 degrees centigrade, and we have a tolerance of about 1 degree centigrade. And finally, we have precise control over the commands we send to DRAM, and this includes the ability to enable and disable self and auto refresh, and also control over different CAS commands, including read and write operations. In terms of our experiment, the goal of our experiment is to infer the ECC scheme in the real LPDDR4 DRAM devices with on-die ECC. And so here I'm going to provide a table of different parameters for experimentation and what their values are in experiment and simulation. The first parameter is word size, and for both experiment and simulation we assume 256-bit words. In terms of ECC schemes, in experimentation, the ECC scheme is unknown. In terms of simulation, we simulate several commonly used ECC codes. For example, Hamming codes, BCH double error correction codes, BCH triple error correction codes, and repetition codes. And in parentheses, we show the data word lengths. In terms of data pattern, for both experiment and simulation, we experiment and simulate with the random data pattern. And in terms of simulation, we also simulate the all ones data pattern. And finally, the error mechanism in both cases is data retention errors. Finally, I'm going to cover our map estimation methodology. So we assume a uniform prior distribution, and we do this because it avoids biasing the results of our map estimation towards any preconceptions we might have as to which ECC scheme is more likely. As an added benefit, it also demonstrates EIN's performance in the worst possible case, where we don't know anything about which ECC scheme is more likely. We simulate 10 to the 6 ECC words per ECC scheme that we evaluate, and this essentially means 10 to the 6 Monte Carlo samples. And we also estimate error using statistical bootstrapping with 10,000 samples per scheme. So now I'm going to show the results of our map estimation. And here along the y-axis, instead of just the likelihood, I'm actually showing the negative log likelihood. And this is for sake of convenience. And what this means is that a lower value on the y-axis means that a scheme is more likely. Along the x-axis, I'm going to show many different ECC schemes that we consider. And I show them by the number of code bits, the number of data bits, and the number of errors correctable as a triplet in parentheses. So here I'm showing a BCH double error correction code with data word length 32 and full code word length 44 bits. And so now we notice that at the top in black we're showing the confidence intervals, and the confidence interval is very tight. So now I'm going to show the 8 most likely schemes in our analysis, and these range from different BCH codes to Hamming codes, and we see that a Hamming single error correction code turns out to be the most likely ECC scheme, and this Hamming error correction code has 128 data bits and 8 parity bits. This means that all of the other schemes shown here are less likely models than the most likely ECC scheme. We have 2 major takeaways from this. First, EIN effectively infers the ECC scheme in the LPDDR4 devices with on-die ECC to be a 128 plus 8-bit Hamming code. Second, EIN infers the ECC scheme without any visibility into the ECC mechanism, without disabling the ECC mechanism, and without tampering with the hardware in any way. So one thing to note is that EIN applies beyond just on-die ECC. So EIN technically applies to any device for which there's a communication channel protected by ECC. We can induce uncorrectable errors, and those errors follow predictable statistical characteristics. And 2 examples of such devices are DRAM with rank level ECC and flash memory ECC. So in the paper, we make many other contributions that I didn't have time to go into here, and I'm going to highlight some of the more interesting ones. So we use EIN in the paper to infer the data pattern and the pre-correction error characteristics, in addition to just the ECC scheme as we showed in this talk. We also provide 2 error characterization studies that show EIN's value in practice. The first shows that EIN enables comparing bit error rates of the DRAM technology itself between the devices with on-die ECC and the devices without on-die ECC. And second, we show that EIN recovers expected distributions that ECC obfuscates. And in the example in the paper, we show that it recovers a temperature versus error rate distribution. We also provide a formal derivation of EIN and a discussion of its limitations. And finally, we verify uniform randomly spaced data retention errors experimentally, and this involves reverse engineering several DRAM design characteristics that affect the uniformity, including the layout of true and anti-cells, for example. Now I'm going to end with a quick recap of the talk and the paper. And so the motivation for our work is that experimentally studying DRAM error mechanisms provides insight for improving performance, energy, and reliability. And the key problem we're facing is that on-die error correction makes studying errors difficult. And this is because on-die ECC distorts the true error distributions using unstandardized and invisible ECC functions. And this means that the post-correction errors lack the insights that we're looking for from the pre-correction errors. Therefore, our goal in this work is to recover the pre-correction information that's masked by on-die ECC. And to this end, we make three major contributions. First, we propose EIN, or error inference, which is a statistical inference methodology that infers the ECC scheme and the pre-correction error characteristics beneath the on-die ECC mechanism. And furthermore, EIN works without any hardware intrusion or insight into the ECC mechanism. Second, we provide EINSim, which is an open source tool for using EIN with real DRAM devices. And third, we provide an experimental demonstration using 314 LPDDR4 DRAM devices that shows that EIN effectively infers both the on-die ECC scheme and pre-correction error rates. And we very much hope that both EIN and EINSim enable many valuable studies going forward. This concludes my talk. Thank you for listening, and now I'm happy to take any questions.